guest speaker today is joining us from his home in Virginia. He has served on more than 20 scientific advisory panels for NASA and the National Science Foundation. He is the author of 70 articles in professional scientific journals dealing with chemical analysis of Apollo lunar samples. John retired as a professor at the distinguished rank from the University at Albany in the late 2016. He is currently residing in Williamsburg, Virginia, where he continues to publish new research. He's one of my favorite presenters, and his enthusiasm is truly infectious. So please welcome John Delano.
Thank you very much, Gloria. It's great to be here, and thanks very much for inviting me. Today, we're going to look at NASA's search for life beyond Earth. It is an exciting field. Information is coming in like water from a fire hose, and we'll try to give you a broad overview of some of the really exciting things that are happening. I have an ambitious goal for the presentation, and it's shown here, where we'll be looking at an introduction, a search for microbial life in our solar system, an overview of the Milky Way galaxy, finding planets around other stars, observing important features about those planets, such as, are they habitable? Might they have life? Looking for biosignatures and technosignatures, signatures that could be arising from technologically advanced life forms on such worlds, and then followed by a summary. So what we'll do is get started with an introduction. This is an overview of the field of astrobiology that was really started by NASA about 20 years ago and has really blossomed on a global scale for many nations. It's a multidisciplinary science with a goal of understanding the origin, evolution, and distribution of life in the universe. Clearly, this is something that'll keep a lot of us busy for quite a while. It is multidisciplinary, as I mentioned, involving in a major way, the six disciplines that you see here in the lower right. Of course, it's underpinned with this fundamental question that has been asked by human beings for many centuries. Is anyone else out there? First of all, let's try to imagine what it is that's made Earth so hospitable for sustaining life, but also for perhaps causing life to form in the first place, especially complex life. First, and keep many of these aspects in the frontal lobes as we go through this presentation. In order to form complex life and sustain it, you need a stable, long-lived star, and the sun is one of those. The sun has a lifespan of approximately 10 billion years. The solar system, our solar system, has been around for a bit over 4.5 billion years. So we still have many billions of years of a stable star that we orbit. It is also helpful to have a circular orbit so that the planet has a similar climate throughout its entire orbit, as opposed to a highly elliptical orbit, where sometimes it's very close to the star and other times it's very far away from the star. Earth has nearly a circular orbit. We need to have a large enough mass of the planet so that it can hold on to an atmosphere. In order to hold on to that atmosphere, you also need a fairly substantial magnetic field. In the absence of that, high energy particles from the star can erode the atmosphere, blast it away over billions of years. The moon has also been an important aspect of causing the Earth to be in a relatively stable orientation with respect to its tilt. We have a tilt, as you know, of about 23, 24 degrees. And the reason it doesn't vary much outside that range is because of the moon. Mars, for example, does not have a moon. does not have a large moon, and it has a very large range of axial tilt, which dramatically affects the seasons on Mars over hundreds of thousands of years. For complex life, oceans and land are useful, have been on Earth. The development of an atmosphere, as we'll mention at the very end, having a high abundance of molecular oxygen. And also plate tectonics, geological activity that allows for complex element cycles. The atmosphere of Earth, for example, has complex cycles, carbon cycles, oxygen cycles, and so forth, that are vital for sustaining life on this planet. So in terms of why it is that life on Earth, complex life on Earth, has been sustained for at least for 500 million years, that's complex life, these aspects have been important. Recent events, unidentified aerial phenomenon, might be considered possible constraints, possible information to be folded into our search for life beyond Earth, as well as I'll mention, this interstellar object that came through our solar system in 2017. First, you're probably all familiar with this Defense Department video.
Dude, that is a fucking drone, bro. There's a whole fleet of them. Look on the ASA. My gosh. They're all going against the wind. The wind's 120 knots from the west. Look at that thing, dude. That's not our LNS though, is it? It's not. That is an LNS, dude. Well, if there's like another thing, it's rotating.
Those were U.S. Navy pilots flying an FA-18 off the deck of a U.S. carrier off the west coast of the United States. They picked this up and followed it, and it was doing things that our current technology is not thought capable of doing. And it gave rise to a preliminary assessment of unidentified aerial phenomena that was recently published by the director of the National Intelligence Agency. And the executive summary makes the following points. There's still a limited quantity of a limited amount of high quality data on these phenomena that hamper our ability to draw firm conclusions about what these things are. In a limited number of incidents, unidentified aerial phenomenon reportedly appeared to exhibit unusual flight characteristics. There are probably multiple types of UAPs requiring different explanations based on the range of appearances and behaviors. And finally, these phenomena pose a safety of flight issue and may pose a challenge to US national security. What they are, could they be objects from other civilizations beyond our solar system? Is certainly one hypothesis, but clearly the Department of Defense and NASA are clearly interested in what these things could be. In October of 2017, an object, the first object to be observed coming from outside our solar system, swept through our solar system at very high speed. And its trajectory looks like what you see here. And a number of hypotheses came out as astronomers began observing it with high quality instruments on it as it was leaving our solar system. And one of the controversial hypotheses, but a very interesting one, that seemed to satisfy most of the observational data, but not in a unique way, was done by Professor Avi Loeb, former chair of the Harvard Department of Astronomy suggested that it was consistent with this object having been a light sail, an artificial object that had come from another space, another civilization somewhere else in the galaxy, that had been flying through in between the stars for hundreds of millions of years until it just happened to stop by, sweep past our solar system. Loeb and his co-workers coined the following phrase, which is startling for its concept. And here it is: space archaeology. I think that, wow, what a mind stretch. The possibility that there could be objects in interstellar space that could serve as points of study by space archaeologists, debris from other solar systems. Again, I'll simply underscore, this is a minority hypothesis that has captured a great deal of criticism from most astronomers, but nonetheless, I mention it here because it's a mind stretch. The next step in our outline is to search for microbial life in our own solar system. And of course, as you know, NASA is keenly interested in that, where Mars is the focus of much of that. This slide here simply compares the relative sizes and relative gravitational accelerations on the Earth compared to Mars. Of course, Mars and Earth never get this close, but this slide is simply showing their relative sizes. Mars is very small compared to Earth and has been losing its atmosphere because of its weak gravitational field and low, probably absent, magnetic field. Mars has been losing its atmosphere for billions of years. Here's a self-portrait of Mars rover. We have 2 active rovers like this on Mars currently, and it is exploring a large crater that formed about 4 billion years ago and was the site of a lake. So this rover is bristling with lots of very interesting, superb instruments for detecting the chemical and isotopic compositions of the atmosphere and of the rock and of the soils. And we know that at this time, about 3.5 billion years ago, when this lake existed, the pH of the water in this lake was close to neutral and existed for tens of millions of years. But additional information is coming in weekly. One of the things that it's doing is drilling samples of rock and putting them in these sample tubes that are about 6 inches in length. They are being put back onto the Martian surface for later retrieval by a joint European-American spacecraft that will land in the same region, pick these sample tubes up, and return them to Earth, where they can be analyzed with the best analytical equipment on the planet when they get back. Perhaps in less than 10 years from now, that mission will fly. Still no launch date determined. Another area of interest for microbial life in our solar system, the possibility of it, is in this icy moon, Europa, orbiting Jupiter. This is what it looks like. Ice covered. The layer of ice is above a large ocean on this planet, on this very large satellite, a bit smaller than our moon. But you also see in this color enhanced photograph from the Galileo spacecraft, we have these tan colors. Those tan colors are salts that have been precipitated on the surface of this icy surface of Europa when water from underneath that shell of ice has been erupted onto the surface. The water has gone off into space and left these salts deposited on the surface. There is a saltwater ocean underneath this layer of ice on Europa, and it is being kept warm. Therefore, NASA will later this year launch a major robotic spacecraft called Europa Clipper to venture to Jupiter and study Europa, looking for evidence of microbial activity from the instruments on board, and better understanding the thickness of that ice cap and how we might go about sampling the ocean in more detail. This is what it looks like. It's about 100 miles across here. See a heavily fractured, icy surface, and then these dark bands of gypsum salts forming that color on Europa. Finally, the other place that's being explored actively is this very tiny satellite orbiting Saturn known as Enceladus. It's only 313 miles across, really a very small place, but remarkably, it was found to have geysers. And this is an image from the Cassini spacecraft that was orbiting Saturn. Notice these plumes going out over 100 miles, plumes erupting from this region of Enceladus. Cassini was programmed and successfully passed through those plumes and measured through spectrometers on board some of the chemical constituents that were in those plumes. And you can see that ammonia, formaldehyde, carbon dioxide, water, and other compounds were erupting from the ocean, again, underneath this ice-capped planet. It too is being kept warm and may be a location for microbial life underneath that ice. Well, that's what we're looking for in our own solar system. You can see that microbial life is the only kind of life that's being looked for within our own solar system. It would be nonetheless fascinating to learn whether life has formed independently elsewhere beyond Earth, even within our solar system. That would have profound implications if that is found to be the case. The Milky Way galaxy, here is an artist's view of it. We live in a large galaxy, 106,000 light years in diameter. 1 light year is 6 trillion miles across. That's 6,000 billion miles per light year, Multiply that times 106,000, and you're looking at a lot of landscape. So we are on a sun orbiting this galaxy, taking us about 200 million years to make a single orbit of our galaxy. It consists of about 250 billion stars. And to give you some sense of that, we're going to show you a video of the neighboring galaxy, the Andromeda galaxy, which is 2.5 million light years away and a bit larger, with about 4 times the number of stars that our Milky Way has. But we're going to take a look at it. Again, as shown at the top, it's about 2.5 million light years away. It's our nearest galactic neighbor. It's 15 million trillion miles away. And keep in mind that as you look at this series of images taken by the Hubble Space Telescope of Andromeda, keep in mind that every speck is another star. And those stars are typically about 20 trillion miles apart. We now know, as you will see later in the talk, that most of those stars are most likely have planets orbiting them. So as you look at all these stars in the Andromeda galaxy, which is a really nice representative of spiral galaxies in our universe, keep in mind that for every speck that you see that it's a star, there are most likely planets orbiting every one of those specks. Now we're going to take a real close look into the Andromeda galaxy. Every speck is a star. Really mind-boggling. And now we're looking at distant views of the universe, this from Hubble, and this from the James Webb Space Telescope, looking out billions of light years, in which every speck that you see in this image, every speck is a galaxy. And the volume of space that you're looking at here is comparable to you're holding a grain of sand between two fingers at arm's length. That is how much sky is being photographed here. Imagine then if you use this and spread it across the entire sky, how many billions of galaxies there are in the universe. An amazing concept. So let's cut to the chase. Yes, there are a lot of stars in our galaxy and over 100 billion other galaxies. But how do you find planets? After all, that's where life will be on planets. So the 4 major methods that are currently used to find planets orbiting other stars are shown here. And we're going to focus on number 3, called the transit method for finding extrasolar planets, which are abbreviated as exoplanets. So here, what you're seeing here, not to scale, not even NASA can build a spacecraft bigger than the Earth, but here is Earth orbiting the sun, and the Kepler spacecraft was orbiting behind the Earth. And notice that it is rotating 4 times each year to make sure that its blue solar panels are focused, collecting energy from the sun. But notice that it is pointing in the same direction all the time. The reason was it was focused on a specific area of the sky, and this is what the various cameras on that telescope were seeing. And we'll take a look at this area shown in the white box, and this is what it was seeing. And you say, well, good grief, what's that? Well, those are all stars. Well, what was it looking for? It was measuring the brightness to a gnat's eyelash of every star every 15 to 20 minutes, recording that information, storing it, and sending it back to Earth by telemetry. Measuring the brightness of all those stars, what could it possibly be looking for? Well, it was looking for planets, and here is an artist's view of our own galaxy. And most of the planets that it found, and I'll show you how they found it, most of them were found within the small circle labeled the sun at the center, and within about 300 light years of the sun. So that incorporates an area. That small circle shows how much of the galaxy was being explored by Kepler. A representative sampling of stars, but lots of stars elsewhere in our galaxy, but nonetheless a representative sampling of stars. What it was looking for is changes in the brightness of those stars. Every star being measured carefully for its brightness, looking for dimming, looking for variations in the brightness of those tiny specks. And it was looking for things like this. Now, here is an image from Earth of our sun on June 5th, 2012. Notice that small black dot at the tip of the yellow arrow. That's the planet Venus. As seen from Earth, Venus went across the face of the sun as viewed from Earth, and it caused, of course, the sun's brightness to dim because Venus got in the way. Is that what Kepler was looking for? That kind of a process? Yes, that's what it was looking for among those hundreds of thousands of stars that Kepler was measuring. And in this case, it took Venus 6 hours and 40 minutes to move along that track of that yellow arrow across the face of the sun. So there was 6 hours and 40 minutes of very slight dimming of the sun during that transit event. It was only 0.000076 or 76 parts per million dimming caused by Venus moving in front of the sun. But that's what Kepler was looking for, that level of dimming. Holy mackerel. Who else can do that? Nobody. NASA can. So here it is. This is an animation of what something might look like, in which a planet, here a very large one, moves across in front of a star, causing a dimming. Dimming. And it takes hours for these transit events to occur, so there's plenty of time for the instruments to collect it. As shown at the bottom of this screen, as of today, 5,569 exoplanets are currently confirmed, with an additional approaching 10,000 that are suspected, and additional data are being acquired on those to try to confirm the presence of them. But at least 5,569 exoplanets are currently known, confirmed, orbiting other stars. Here are data from Kepler showing you what a light curve looks like for a planet transiting a star. And here it is. Notice planet was not in front of the star. It was at 1 normal brightness of the star. And then the star dimmed. And over the course of 2.89 hours, a planet went across in front of that star and then moved away from that star, no longer in front of it. The orbital period of that planet, when you watch that star, you would see it again, and then you'd see the transit again, and then again. And the period between those repeated transits is shown by the orbital period. Note, not only do you see a planet orbiting that star, but the size, the depth of dimming gives you the size of the star, and the repeat of the transit events gives you the orbital period of that planet. So this orbital period is known pretty well, as you can see, 4.72673978, plus or minus a very small amount of Earth days. That means the orbital period of this particular planet is known to plus or minus about 1 second, as an orbital period of just under 4 3/4 days, Earth days. A follow-on mission to Kepler was successfully sent by NASA. It's known as TESS, Transiting Exoplanet Survey Satellite, and it was launched in 2018 and has been and continues to be very successful in looking for and finding other planets orbiting other stars. Whereas Kepler had focused on a single area of the sky, TESS is doing a virtual all-sky survey looking for exoplanets. Here is how the discovery of exoplanets has gone. Back in 1995, the x-axis is years, and the y-axis is numbers of exoplanets confirmed. In 1995, the first planet orbiting another star was confirmed by Earth-based telescopes, and the 2 investigators shared a Nobel Prize for their outstanding path-breaking work in finding that first planet. And notice how the numbers of planets have grown since then, so that in 2003, we were just over 5,500, and as of today, it's 5,569 confirmed planets. So you can see the discovery of exoplanets has really soared since the launch of Kepler and TESS, as well as outstanding ground-based astronomy. Here's what it looks like. You're looking at 5,569 points on this graph, in which we're plotting here on the x-axis the size of the orbit. How far away from the star do these planets orbit their star? And the x-axis shown here at 1. The value of 1 on the x-axis means that that a planet orbits its star at the same distance that Earth orbits the sun. Notice that most of the planets orbit their stars much closer to their stars than Earth does. The y-axis is the radius of the planet compared to Earth. Earth has a radius shown on the y-axis here is 1. And the first red line that you see here, the lower red dashed line, is the boundary between things that are called Earth-sized and things that are known as super-Earths. These are all rocky worlds. Earth, for comparison, is shown by the red star in the lower right of this diagram here. So Earths and super-Earths are rocky terrestrial type worlds. Notice that there are a lot of worlds above that second dashed line. Those are Neptune-sized worlds. They're gas giants. And maybe ocean worlds as well. And then you get into the Jupiter and larger sized planets known as the Jovians. This is what a representative sampling of stars looks like with respect to planets. Earth-sized planets, so far you can see that they are quite abundant. Super-Earths, for which there are no super-Earth planets in our solar system, notice that they are really abundant. There are hundreds of them in between those two lower dashed lines. They are the right size for satisfying one criterion for being habitable by life as we know it. Observing important features of exoplanets for the next piece of our journey here. Observing important features of exoplanets. How many of them are in what's known as the Goldilocks zone, or the so-called habitable zone? The habitable zone is shown in this previous one, in which we have a campfire and people are sitting around the campfire. If they were further away, they'd be cold. If they were closer than they are to this campfire, they'd be too hot. So you can see this ring of campers around this campfire are sitting in the habitable zone of that campfire. The analogy here for planets orbiting a star, which is giving off a lot of heat and energy then, is shown here, where you have a star in the center. And for Mercury, the innermost planet in our solar system, again, this is not to scale. Mercury is too close to the star. It's much too hot. Venus is on the inner edge, possibly, of a habitable zone. And notice these various shades of green are the estimated habitable zone, the distance from the sun where planets could possibly have conditions that are suitable for life as we know it. And you can see that Earth is right in that darker green area. We're in the habitable zone, of course. The simple equation that's used to determine the distance of a planet from its star, remember, we're only looking at dipping of light. The brightness of a star as a planet goes in front of it gives you the size and the orbital period, but knowing the mass of the star and the gravitational constant, and you measure P, the period, how frequently do those transits occur, the orbital period. You can then solve for A, which is the distance that the planet orbits from its star. It's Kepler's third law. And this is what we're seeing here. Here are those planets, again, 5,569 planets as of today. And on the orbital period in days, 1, 10 days, 100 days, 1,000 days, and M for at the lower right here is Mars. The red star is Earth, Venus, and Mercury. And again, those 5,569 exoplanets are shown here. The y-axis is insolation, in which 1 is the quantity of energy that we on Earth get from the sun. If you have higher insolation, then you're getting more energy from the star than we get from the sun. So it gets hotter. And the higher the value of insolation, the hotter that planet is. If you're less than 1, you're getting less energy from that star that you're orbiting than what we get for comparison from our sun. And notice that most of the planets that are found so far have much higher insolations than the Earth. Our habitable zone for life as we know it is somewhere between where Venus is and where Mars is. And the values of the insolation are shown by those 2 dashed black lines. And notice that there are other planets that have been found, dozens of them, that fall between those 2 dashed lines. And the ones in here with very short orbital periods measured in single days have similar insolation values, and they're just orbiting very small, dim stars, but they're getting the same amount of energy from their star as we are from our sun. They are habitable from that point of view. Here's an illustration as we approach the end of the talk today. The so-called TRAPPIST system, located about 40 light years from Earth. A very small, dim, red star, but with a host of 7 Earth-sized planets. Remarkable. 7 Earth-sized planets, all of them rocky, orbiting that dim star. Now, because it's a small, dim star, these planets are orbiting very close. So here at the bottom here is, for comparison, our solar system, our inner solar system, showing the orbits of the Mercury, Venus, Earth, and Mars. And the TRAPPIST system would fit within that small area shown as I'm trying to circle at the bottom left of the screen, could fit within that area there. But because it's a small, dim, red star, some of those planets orbiting TRAPPIST, showing here, B, C, D, E, F, G, and H. You can see that D and E fall within the habitable zone of that star. They could be habitable and are now a focus of part of the work that the James Webb Space Telescope is doing to find out whether they may, in fact, have an atmosphere, and whether that atmosphere, as I'll show in the next slide, has any indications of life being present on those planets. So here is a cartoon, an artist's view of what TRAPPIST D or E might look like in that habitable zone. An ocean with a reddish star within the habitable zone, and with oceans lapping on the shoreline. Perhaps this is what it might look like. But the James Webb Space Telescope is actively now trying to analyze the atmospheres of those planets. It is looking for biosignatures and technosignatures, evidence signature, chemical signatures of whether biology exists from the chemical composition of the atmospheres, and looking for signatures in the atmospheres of whether technology exists on those worlds. The James Webb Space Telescope is a marvel. And here's a scale model of it. Again, people for scale. And here is the James Webb Space Telescope mirror compared to a technician, shown here on the right side. You can see it is a gigantic telescope, the largest that has ever been launched. It's a European space agency and NASA effort has brought this to fruition. And here is what they're trying to do. When a planet orbits in front of a star, not only does it transit, but some of the sunlight passes through the atmosphere, shown here in this blue ring around this hypothetical planet. As the starlight passes through the atmosphere, it carries with it a spectral signature of some of the molecules in the atmosphere. You measure the photons by that telescope, you measure the photons which have visited that atmosphere and interrogate those photons to find out what kind of stuff is there. Finally, a recent article just published a couple months ago suggests that one of the molecules that should be looked for in these exoplanetary atmospheres for the possibility of technosignatures is molecular oxygen. And the rationale for that is shown here, and I'll read it very quickly. Only planets with substantial oxygen in their atmospheres will be capable of developing advanced technospheres, and hence technosignatures that we can detect. Open air combustion, needed, for example, for metallurgy, is possible only in Earth-like atmospheres where oxygen is greater than 18%. And of course, our atmosphere has about 21% oxygen. This limit is higher than the one needed to sustain complex biosphere and multicellular organisms. But the presence of at least 18% in an exosphere, an exoplanetary atmosphere, may be useful for planning and interpreting technosignatures searches. The idea here is technologies will not advance unless complex animals, develop fire. And without sufficient oxygen, you cannot burn things. Summary then, real quick. The universe, as you've seen, you've gotten a glimpse that it not only is an ancient, at least 13.7 billion years old. Our solar system is about a little over 4.5 billion. The universe is 13.7 billion. The universe is ancient and unfathomably vast. The possibility for life beyond the Earth seems to be enormous. The Milky Way galaxy is ancient, vast, and has billions of planets. I'll quickly overview these planets. Planets are now, we know. 1995, we had no idea. Now we know that planets are common and are incredibly diverse in the galaxies. Planets less than 10 times the mass of the Earth are common. The current estimate for the number of habitable planets in our galaxy is somewhere between 1 billion and 10 billion habitable galaxies in our galaxy. Most planets do not have highly circular orbits. Most are more elliptical than ours, but nonetheless still could be habitable. Characteristics that define habitability include living in the habitable zone, the Goldilocks zone being around long-lived stars, absence of tidal lock, those I didn't mention but will now. Most of the planets, all of the planets orbiting the TRAPPIST system, although they are in the habitable zone, they are all tidally locked. Tidally locked. Only one faces their star forever. And the James Webb Space Telescope has already measured looked for the presence of atmosphere on the two inner planets of the TRAPPIST system, and those two inner planets do not have atmospheres any longer. If they started with them, they don't have atmospheres now. I close then with this familiar voice.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find it. We have uncovered one.
Thank you very much. We live in very exciting times.
Thank you, John. And now we'll take questions. If there's anybody here in the audience that has one, just raise your hand and we'll get a microphone to you.
That was extremely interesting. What is the current thought on the size of the universe? James Webb is finding black holes and other galaxies that seem to be formed before they should. If the Big Bang was 13 billion years ago, or whatever. So what is the current thought?
Did you get that?
I think I could hear the question well enough. The James Webb Space Telescope is indeed finding some remarkable things. The galaxies, based on the current models before James Webb was launched, the galaxies that are being found are too many, too well organized, too large, have too many stars, are too orderly, and have chemical compositions that are more evolved than had been predicted. Other than that, everything's fine. Your point is very well taken. Science is exploration. We try to learn things. How boring it would be if we found that James Webb found everything that we were expecting to find. In fact, holy mackerel, it is not. So the jury is still out. Many scientists are losing sleep as they try to figure out what this is, whether the age of the universe is greater than 13.7, which is what it currently is suggested as being. The early evolution of the universe is up for grabs. Your point is well taken. Stay tuned. James Webb is doing exactly what it was planned to do. Help us learn new things.
So we've got a question from the chat box, and let's see if we can. Can you hear Liz?
Barely, yes.
What proportion of stars in the universe have any orbiting planets, and what proportion is habitable range?
Hang on a second. Maybe we can bring it up.
I have the chat box up. Let's see.
Can you see it?
I can see the chat box.
Okay.
The question that I see in front of me is I have heard that there are exoplanets with organic molecules in their atmospheres. Were these preliminary or confirmed? If that's one of the questions of interest, the answer is yes, they have been confirmed, but only in a general sense. Carbon dioxide has been observed, but what is most remarkable, and hold the phone if this is confirmed, what was found in the spectra of one of the super Earth mini Neptune-sized planets, possibly an ocean world, an ocean-covered world, is the possibility of methyl disulfide. If that molecule is confirmed by additional observations, we know how methyl disulfide forms on Earth, and it's formed by ocean life, microbial life. And if there is microbial life broadly similar to what we have on Earth, it could be forming methyl disulfide in dimethyl sulfide in the atmosphere of that exoplanet. Hold the phone. If it is confirmed, we have found indirect evidence of life on another world.
Any questions here?
John, can you hear me?
Barely.
Okay, I'll speak up as I can. This is a policy question in a way. Are we spending enough money and deploying enough resources to keep up with our intellectual, venturous, otherwise developed capacities?
Are we spending enough money to remain competitive?
Not competitive, but to make use of all that's being understood or discovered or opened up. Could we be doing more faster?
We certainly could be doing more faster. Yes. NASA, for example, just as an illustration, NASA has a federal budget that is slightly less than 1% of the federal budget. In comparison, during the peak of the Apollo years, where we wanted to beat the Soviets to the moon, the United States was spending 3.5% of the GDP. I would say 3.5% of our federal budget was going toward NASA during our effort to get to the moon ahead of the Soviets. Now we're spending less than 1%. So if we really wanted to up our game, certainly NASA and National Science Foundation and NIH would be ways of doing it. But we are currently, of course, running big deficits. It's a judgment call.
So John,
I'm working with the Chinese scientists on analysis of the samples they retrieved from the moon, and they are going like gangbusters.
John, I think there are more questions in the chat box. Do you want to read the second one?
Okay. One I'm looking at here is what proportion of stars in the universe have any orbiting planets, and what proportion is the habitable range. The idea so far is that most of the low mass and medium mass planets, probably roughly 2 out of every 3 of them, which are the majority of all stars, 2 out of every 3 of them probably have planets. So we're looking at multi-billions of planets in our own galaxy. What proportion is in the habitable range? Again, it's a lot more data are needed, but currently the number that are thought to be in the habitable zone in our galaxy is somewhere between 1 and 10 billion rocky planets within the habitable zone in our own galaxy. But that number is changing as more data come in.
Any questions from the audience here? Okay, we have some more in the chat box.
Very specific. Why are there two ends on the orbit insulation graph?
One of the questions I'm looking at are why are there two M's in the orbit insulation graph? The two M's, and I will see if I can scroll back to that insulation graph. One of them, the lower right, is the location of Mars, and the other one further up, diagonally to the left, is Mercury. So one M is Mars, and the other M is Mercury.
And that's it. Okay. Okay, what keeps galaxies from disintegrating and what exists disaggregating rather, and what exists between galaxies?
Yes, I'll go back to the slide showing the galaxies. Gravity holds these galaxies together. They are in orbit. All of the stars in this galaxy here, the Andromeda galaxy, are in orbit around a large central mass that is glowing brightly here because a lot of stars are there. That's a black hole. A massive gravitational force is coming from the black hole, which is gravitationally holding that galaxy and our galaxy, holding it together. Gravity. So you're looking at this picture here at about the glow from about 1 trillion stars, all of them in orbit around a tiny central mass consisting of millions of times the mass of the sun. So gravity is what keeps us in orbit around the sun. Gravity is what holds the moon in orbit around the earth. Gravity is what does all the work.
We have a question from the audience.
Is there a black hole in the center of our galaxy?
Is there a black hole at the center of our galaxy?
Yes, there is. Yes, it is. And it has been studied and continues to be studied to better understand how massive it is, but it involves a very small size in terms of space, in terms of diameter, but something less than the size of our own solar system, but tens of millions of times more massive than the sun. And we are about 30,000 light years away from that black hole. So we're not about to fall into it. We've been in a nice stable orbit in our galaxy for billions of years. So we're safe.
I had one question. As black holes consume neighborhood stars and their mass increases, does that change the dynamics of the galaxy?
As the black hole consumes mass, does it change the configuration of the galaxy? It must, and I'm sorry, I'm not a galactic astronomer, so I'm going to have to wing it here. Yes, that would have some modest effect on the area closest to the black hole, but I wouldn't be able to talk with great confidence about anything else. I'm sorry to say.
Can you come back next week?
They want to know if you can come back next week.
Is there snow?
Yes.
There's just so much data coming out. It's just fantastic. It is fantastic. So just stay tuned for scientific results that may ultimately lead to a detection of a biosignature, or remarkable, even a technosignature in the atmosphere of an exoplanet. Already, dimethyl sulfide has been detected. It appears on one exoplanet, but scientists are being very, very cautious about saying that that is a positive life detection. But by golly, if that is confirmed, oh, wow.
So I see another question popped up in the chat box there.
Oh, what is WASP 39b? That's from Dave. I'm sorry, I have trouble keeping nearly 5,500 exoplanets between the ears, and I'm sorry. You and I will have to Google WASP 39b.
So I guess that's it. I want to thank you, John. Fascinating.
Thank you very much, Gloria. Thanks to everybody. Look forward to being there next week.
We would love to have you back, and it would be great if you could be here in person, actually in person. So, and I want to thank everyone here for joining us. So thank you.
Thank you.